Good morning. My name is Michael Wegerson, and I'm actually an undergraduate student from the University of North Dakota. So it's a wonderful presentation to follow. As I mentioned, yes, I'm an undergraduate student studying electrical engineering, and this morning I'm talking about the development of an open source software-defined radio for the Open Orbiter project. But let me begin by first discussing the outline to my presentation. Starting off, I'll discuss the background to the Open Orbiter project and some of its goals. Following that, I will talk about the communication subsystem, the subsystem I'm working on, and the research we've done into software-defined radios and how those satisfy some of the Open Orbiter goals. After that, I will talk about the current implementation of our software-defined radio, including the hardware and software components. Following that, I will talk about the results to date that we have achieved with this radio implementation and also some of the challenges we are still facing. And wrapping up, I will discuss some of our plans for the future of this project as well as my conclusion. So, without further delay, let's begin. The Open Orbiter project, well, it stands for Open Prototype for Educational Nanosatellites, OPEN. It is the University of North Dakota's CubeSat project that began in November 2012. It is a student-led project, but faculty advised. And we are currently developing a 1U CubeSat. And when launched, it will be North Dakota's first satellite, so yay. The main payload will be photo capturing. We are testing some software for photo mosaicing and super resolution, but this is not the main focus of the project. The main focus of the project is to make a low-cost and versatile framework that will be open for public use. So with this in mind, we are using consumer off-the-shelf parts to allow for a low cost of $3,000 to $5,000 USD. And it will include all subsystems, attitude determination and control, power conditioning, and of course communications, and etc. With an open area for a customizable payload that can be easily integrated into the existing framework. The reason why we're doing this is because universities such as ours, we spend a lot of time developing the framework for the CubeSat, the subsystems, and we spend a lot of time and money developing the frame. And in addition to spending money for developing the scientific experiments. And this is a huge upfront cost for universities, and it may dissuade some universities from participating. So by making our design open source and available to the public and low cost, we can assist these universities by providing them with a framework that they can then spend more time, energy, and money in developing their own payloads. And then moving on to the communication subsystem. We decided to go with a software-defined radio implementation because this allows for additional flexibility and potentially low cost. And what an SDR does is it essentially replaces hardware components in a traditional radio setup with software configurations that can configure the radio in real time. So that includes things like switching frequencies and modulation types and bandwidths. And this is good for the unpredictability of space. And of course, we'd also like it to be open source so the end user can modify it to tailor to their specific mission needs. But several considerations we had to take into fact with our own project is the bandwidth. We had to consider enough bandwidth to transmit high-resolution photos for our mission. And also we had to consider the amount of battery. We didn't quite know how running software instead of hardware would play on battery usage. So after researching several alternatives, we actually ended up with our current implementation, which is surprising because it turned out to be quite convenient. For our primary transmitter, we are using the Raspberry Pi microcomputer. This was already implemented in the design as the primary flight computer, so it seemed useful to attempt to use it as the radio, the transmitter, excuse me. It's able to generate RF signals with proper programming. Some of the details of that are outputting on the GPIO4 pin. It allows, or that pin is responsible for outputting a clock signal, and through clever programming, we are able to create the output up to 200 megahertz, so enough to generate a carrier wave for data. But this is a square wave, so it would require filtering. Some considerations we needed to take into factor was it was very low power, less than 50 milliwatts. This is due to the 3.3 digital logic pins only being limited to 16 milliamps of current, and that number decreases the more GPIO pins are connected. So moving on to the transmission software, we are currently using two different software types. We are using software called PiFM, which is the primary transmission software. It was originally designed to play music wave files, but we were testing it to see if it could transmit actual data. It controls the output clock on the GPIO pin by dividing the main processor clock by a certain fraction to get the desired carrier frequency. And it modulates it over the wave file, or a dot wave file for the transmission. This software is ideal because it has low CPU overhead by offloading the main execution of the program to the Raspberry Pi's BMC. So this allows for 1 to 2% main processor usage. So it allows for the main flight control computer to do flight control calculations, and also lowers the power consumption. And in this instance, the PiFM is acting as the digital audio to analog converter, which I'll show in a later block diagram. Following that, we have a program called Minimodem, and what this does is it takes input data and converts it into a wave audio file that we use to transmit with PiFM. It does this by modulating the data in an audio frequency key shift, so AFKS modulation. And again, this software is open source. So the transmitting block diagram is just kind of the general flow of the data. We start with the input in the input text, a text file, and we modulate that file using AFKS modulation, which outputs a wave file. And from that wave file, it goes into PiFM, which it gets added to the carrier wave, and from there it gets outputted as an analog signal. Through the analog signal, it goes through a custom filter to suppress the odd harmonics that are generated by the square wave that is output by the Raspberry Pi. And just as a general note, the blue squares and the red squares represent the software components and the hardware components of the system. So moving on to the receiver, we are actually using a Raphael Micro TV tuner, which is only 20 USD, so that follows the CubeSat goal with low cost. It's based off the Realtek RTL 2832U chip, which is able to receive a wide range of signals ranging from 24 megahertz to 1766 megahertz. So this wide frequency range is ideal for an SDR. It also has a very high sampling rate. We have tested it at 2 megasamples per second, but it has a theoretical maximum of 3.2 megasamples per second, but that has significant sample drop. And this was used for analog to digital conversion. Further explanation in the block diagram. For our receiving software, we are mainly using GNU Radio as the primary receiving software. GNU Radio is excellent at this as it allows for manipulation of digital signals. We're mainly using it for filtering and audio conversion, but the ability of this software can go far beyond that. And we use this to create to convert the digital signal from the TV tuner to a wave file that can be demodulated by, again, Minimodem. It also can demodulate the audio file back into text. So, again, a general diagram of the receiving block. The information is received by the TV tuner and is converted from the analog to digital signal. From there, it is computed through GNU Radio and through low pass and squelch filters and converted into a dot wave file. From the dot wave file, Minimodem demodulates the file and converts it back into the output text. And again, blue is software and red is hardware. So this is a block diagram of the programming within GNU Radio. This is actually the implementation we're currently using. Again, red is the digital interface for converting and interpreting the data from the TV tuner. The blue are the filters to help process the signal before it's converted to mini-modem, as this helps increase the decrease the data error rate. And the final step is converting it into the digital file. So, enough of the theory. The results to date. So some of the early successes we had with this program was demodulating our first FM signals from a nearby radio tower in early 2012 by setting up GNU Radio with the receiver. And also transmitting data in early spring of 2014. It took us a bit of time to get the transmitter working on the Raspberry Pi. But where we are, there we go. Where we are today. We have tested FM transmissions from 24 megahertz to around 250 megahertz. Signal begins to break up around 200 megahertz and is unusable at 250 megahertz. And we've also tested several different baud rates on the US amateur radio bands of 52 megahertz and 144 megahertz. And we've been successful in transmitting at 300 baud to 2400 baud, with noticeable errors at 3600 baud and unusable at 4800 baud. With the frequency and the filter settings being fully customizable at runtime. And this is, I guess I should drop the slide. But for our testing, we actually used the manual for the Linux Python, or the Linux manual for Python. We converted that into text, transmitted it over, and demodulated it on the receiving end, and compared it with the original file to determine the error rates and so on. Some of the remaining challenges that we still face are the limitations of the Raspberry Pi. Due to its low power transmission, it's unusable for space-ground transmission. It simply just needs more power. Applying an amplifier would limit the frequency range to a specific range, and this would not be a part of the SDR goals that we were going for. And also software limitations. Replacing GNU Radio with mini modem is one of our goals, to create a unified software front that only uses GNU Radio. But some of the other issues we are having are compiling and running GNU Radio on the Raspberry Pi. We're having issues with the RAM usage and it actually crashing. In addition to that, running GNU Radio, we have it currently running on a dedicated laptop, and it struggles to do that, so we were wondering how it would fare on the Raspberry Pi. We also have the potential to run GNU Radio on some gum sticks that we are using for image processing, but then again, that might be too much overhead and power usage. We have additional testing, of course, to do. Another issue is software upgradability. We have run into, when we upgrade the software, Pi-FM and transmission begins to increase in errors, requiring us to modify the code specifically as we upgrade the software. So, going from there, our planned work is high-altitude balloon test to determine the specific range of this potential radio implementation, and to see the low-power range. And some of the work we are going to continue to do is expanding the frequency range of the Raspberry Pi, also increasing the flexibility of the amplifier and the variable filter to increase the signal strength and also filter unwanted noise by increasing the signal strength. We also need to research antenna design, as increasing the frequency range and the efficiency of the transmission is dependent on the size of the antenna. So we're still looking into developing an antenna that will be efficient at multiple different rates. And software issues that I previously described. So in conclusion, SDRs, they're a very powerful and flexible piece of software, but it's not a one-fit solution. It satisfies the goals for our open project, but with the limitations of the software, the receiver requiring a high amount of computing power and the low-powered nature of the Raspberry Pi transmitter, this actually was found to not be a practical solution currently for the Open Orbiter project, mainly due to subsystem integration tests in the middle of next month and the schedule for phase 1 completion for our project at the end of January. So the amount of work and time to get this solution working outspends the amount of time we have available. So we actually had to delay the project to continue working on other critical systems. But nonetheless, we will continue researching when more time is available, and I do feel confident that we will overcome some of these challenges as time progresses. So with that, I would like to thank you for your attention. I would also like to thank the symposium coordinators for accepting my proposal to speak at this distinguished conference. In addition, I'd like to thank the University of North Dakota and the Vice President of Academic Affairs and their support for my attending this conference. Are there any questions?
So we only have time for one very quick question.
I have one. Which license you use for your for the software? Since you mentioned you want to put it in open source, so you should have there some license you want to use, like.
I don't know the specific answer. I believe it's general public license.
Okay. So I guess a new version. Then.
Yeah.
Okay. Thank you.
So thank you again.